All right, let's do some use substitution on definite integrals. So now we are going to need to deal with whenever our limits of integration when our integrals have limits of integration. So things are going to be a little bit different. So the first thing I want you to recognize is that the limits of integration are associated with a specific variable. So in this case, we have that x equals 1 to x equals 4 of e to the x squared 3x dx. And so when we do our substitution, so when we look at this, we have an x squared, and its derivative is 2x, which is close to this 3x. And so let's say that u is equal to x squared, and du dx, and forgive my handwriting, I've misplaced my Apple pen, and so I'm writing with the stylus, so it's not quite as nice as I usually have, is equal to 2x. So du is equal to 2x dx. So when we rewrite this, we're going to have the integral from x equals 1 to x equals 4 of e to the x squared. And then we want it to be 2x dx, and so we're going to divide 3 by 2 times 2x dx. So then when we replace everything with u, I'm going to write this integral, and I'm going to say it's from u equals to u equals. But I'm going to leave those blank for right now. So we're going to have e to the u times 3/2 du when we do our replacement. But we need to replace our limits of integration as well. And what we want to use is what u is equal to in terms of x squared, So if x is equal to 1, then u is equal to 1 squared. And if x is equal to 4, then u is equal to 4 squared. So we are looking at new limits of integration from 1 to 16 with this new style. So when we take the integral, we're going to have the integral of 3/2 e to the u is 3/2 e to the u. And now we're going from u equals, and then 1 squared is 1, and 4 squared is 16. So we're going to have, this is 3/2 e to the 16 minus 3/2 e to the 1. And as far as like a answer goes, then you could either find out what this is in approximate, or we can leave it as is, as an exact answer, because this is an exact answer. Or we could have left our limits of integration the same. So we would have had 3/2 e to the u, but going from x equals 1 to x equals 4, right? But the only thing that now we need to change is we need to change the u back to x. And so it's going to be 3/2 e to the x squared from x equals 1 to x equals 4, which is going to be 3/2 e to the 4 squared, which is 16, minus 3/2 e to the 1 squared, which is 1, which will just end up being the same thing as whenever we changed our limits of integration. Either way is a valid way of using u substitution. So let's do the old u-do. So if we look at our first of the u-dos, then u should be natural log of x, because du dx is going to be 1 over x. Therefore, du is 1 over x dx. So if we go back over here to our original problem, if we want to rewrite it in terms of u and du, then we're going to have, let's start with natural log of x times, and then we want it to be 1 over x dx. To change that into du. So we're going to have a 1/5 out front whenever we factor out the 5. And so if we rewrite this in terms of u, then we're going to have the integral of u times 1/5 du. Okay? And so when you take that antiderivative, we're going to pull out that 1/5 because it's a constant, times 1/2 u squared plus c, and then rewrite it in terms of x because it is not a definite integral. So you have 1/10, so that's 1/5 times 1/2 of u, which is natural log of x, all squared plus c. Now let's do the next problem. So first, let's split this integral across that plus sign. So we've got the integral of 5x e to the x squared dx plus the integral of x squared dx. So we know how to take the antiderivative of x squared. So now we just have to figure out how to do this first integral. So we are going to say for this first integral that u is equal to x squared. So that du dx is equal to 2x. Therefore, du is equal to 2x dx. So that when we rewrite it, we're going to rewrite this first one as the integral of, we want 2x dx, and so we have a 5x, so we're going to pull out a 2, so we're going to have 5 halves, that's 5 halves, times 2x e to the x squared dx, plus, and then the antiderivative of x squared is just 1/3 x cubed. And then we're going to have a plus c at the end there. And then let's go back and rewrite this first integral, and we have 5 halves. 2x dx is du, and so we have e to the x squared is just going to be e to the u du plus 1/3 x cubed plus c. And then the antiderivative of 5 halves e to the u is 5 halves e to the u plus 1/3 x cubed plus c. And then we need to finish it by writing it all in x. So that's going to be 5 halves e to the x squared plus 1/3 x cubed plus c. And that is our answer to the second UDO problem. Now let's go on and do the next one. So I know in the last time I said this, I said that you might have to do more than one U substitution, and you can, but I realized after the fact that you could do it with just a single U substitution. So if we're looking at this problem, then it is kind of obvious that right in here, this cosine of x cubed plus 4 is the inside function of this sign, and it's the more complicated here. However, x cubed plus 4 is the most inside of this guy. And so we're going to do the double U substitution, and then I'll show you what I mean by that. You don't need to do twice. But let's just say that this x cubed plus 4 is our U. So we're going to say U is x cubed plus 4, which means that du dx is 3x squared, which means that du is 3x squared dx when we multiply that dx across. So if we're looking at this, we're going to we rewrite it with our first guy run through. Then we're going to have sine of cosine of u times sine of u. And then we have that x squared. Now, I should have done this in a separate step, but let's just say that this x squared, we want it to be 3x squared dx. And so that's going to be 1/3 times 3x squared dx. And so if we were to rewrite that and substitute that with du, it's going to be 1/3 du. Okay? So then we have this, and we're going to need to do a second substitution. And now this second substitution, I'm going to do in a different color and a different variable. So I'm going to say v. V is equal to, and if we're looking at this cosine of u is our inside function of sine. And so when we go back here, we're going to say cosine of u is our inside. And then when you take the derivative, so dv du is going to be equal to, and then the derivative of cosine is negative sine of u, which means that dv is equal to negative sine of u du. So when we rewrite it, we are going to have, let's see here, sine of u, or of v, sorry, because we're changing it to a different variable, times, and then we have this 1/3 sine of u. And we want it to be negative sine of u. And so to make that negative, we're going to pull out a negative 1/3, because negative 1/3 will leave us with negative sine du. So that's going to be negative 1/3 dv. So that 3 is coming out a little funky. All right, so then this is times negative 1/3, not minus 1/3. So the antiderivative of sine of v times negative 1/3 dv is going to be negative 1/3 times negative cosine of v. So that will be 1/3 cosine of v plus c. And v is equal to cosine of u, so 1/3 cosine of u plus c, and u is x cubed plus 4. So that's going to be 1/3 cosine of x cubed plus 4 plus c. Now, what we could have done, if we wanted to do a single step, and I challenge you to this, would be, or you might want to try this. So set your original u equal to cosine of x cubed plus 4. Then when you take the derivative, your du dx is going to be sine, or negative sine x cubed plus 4, times 3x squared. Oh, oops. What happened there? Okay, du dx is equal to. And then go on and try to solve that on your own and see if you could do it the other way. All right, so let's do a definite integral. And this one's very similar to the first of the last u-dos, except now we have limits of integration right here and right here. So if we're looking at these, then we're going to need to come up with a u to substitute. And from last time, we see that our u is equal to natural log of x. So du dx is 1 over x, and so du is equal to 1 over x dx. All right, and so we're going to pull out that 7th, but you need to remember that these limits of integration have to do with x. So these are x equals e to x equals e to the fifth. So when we substitute back in, we need to remember to change these limits of integration to those in terms of u. And so when we rewrite this, we're going to have from u equals something to u equals something. So when x is equal to e, natural log of e is going to be 1. When x is equal to e to the fifth, then u is equal to natural log of e to the fifth, which is 5. And then we have 1/7 u du. So I just pulled out that 1/7, and then natural log of x turns into u, and then the 1 over x turns into the 1 over x dx is du. And so when you take that derivative, or when you take that antiderivative, then that's going to be 1/7 times 1/2 u squared from u equals 1 to u equals 5. And so this will be equal to 1/14 times 5 squared minus 1/14 times 1 squared. So you're going to have 25/14 minus 1/14, which is 24/14. Okay? So this is how we do this definite integral. All right. Let's look at something a little bit more abstract. So now we're looking at the derivative, or the antiderivative, from x equals 0 to x equals 1 of 8x times g of 4x squared dx. So if we're looking at this, g is an outside function, and the inside is 4x squared. So if we want to use u substitution, then our u is going to be 4x squared, and our du dx is 8x, which means that du is 8x dx. So if we're looking at this, we don't even have to factor anything. And so when we rewrite this integral, we're going to go from u equals something to u equals something. And it is going to be 8x dx is du, and g of 4x squared is g of u du. And then we're going from u equals, and when you plug in 0 into what u is equal to in terms of this, then you're going to have 4 times 0 squared, so it's going to be 0. So u is 0. And then when x is equal to 1, and you plug that into this equation, then you're going to have that u is equal to 4 times 1 squared, which is 4. Oh, I just realized I needed to write this a little different. So if you're going back through, make it a g prime instead of a g. Okay? So now you have the antiderivative from u equals 0 to u equals 4 of g prime of u du. So that when you take the antiderivative of g prime of u, then you're going to have g of u, because the antiderivative of the derivative is g. And we're going from u equals 0 to u equals 4. So when we solve this, the answer is going to be g of 4 minus g of 0. And that's all we can say because we don't know anything else about g prime or g. But you still should be able to do this with something that's a little bit more abstract. Now, what if we need to do something a little bit more, something different? Let's look at something different and tell me if you can tell what's going on. So let's say that we have the, let's do a definite integral of x to the fourth plus square root of x dx. But instead of going from numbers, let's say that we're going from, let's say, theta to, say, e to the theta. All right, so your limits of integration are no longer numbers, but here's the secret. It doesn't change anything on how you solve them. So your limits of integration here, like you just will plug them in the same way. So you're going to find the antiderivative of this and then plug in your limits of integration and subtract them. Now, just to remind you, this might look a little bit like the fundamental theorem of calculus part 2, but it is not. Well, I mean, it is, but it's not that type of problem. Remember, for the fundamental theorem of calculus part 2, you might be given a derivative that you know the antiderivative of, or you'll have that d dx out front. D dx. And if you have the d dx out front, then this becomes even simpler in some ways. I would recommend go back and look at that video. I recommend to go back and look at that video. So let's actually solve this. And so we're going to rewrite it because the square root of x is kind of a challenge. Oh, let's go back to the purple. So we're going to go from theta to e to the theta of x to the fourth plus x to the 1/2 dx. And so the antiderivative of that is going to be 1/5 x to the fifth plus 2/3 x to the 3/2 when you take the antiderivative from theta to e to the theta, which is equal to, I'm going to go to the next line, which is equal to 1/5 e to the theta to the fifth plus 2/3 e to the theta to the 3/2 minus 1/5 theta to the fifth plus 2/3 theta to the 3/2. Okay, so make sure that you put these in parentheses whenever you're subtracting the whole thing. But this is it. I mean, you could simplify it, but we don't really have anything. But that's all you have to do if your limits are weird. You don't have to do anything else. Now remember, if you had to do some, like, let's suppose that the thing on the inside here was more complicated and you had to do u substitution, then you would have to change these limits of integration because this is from x equals theta to x equals e to the theta. So if you were to change this to a u and you had a u substitution, you'd have to go back through and change those limits of integration before you continued.